In this section, we're going to look at a special type of differential equation called a homogeneous differential equation. And we're going to start with the definition for a homogeneous function of degree n. What it says is that if we plug in t times x and t times y, where t is a real number, then if it's homogeneous, that's the same thing as having t to some power times the original function. So we're looking at, is this function homogeneous? To tell, we plug in and find f of tx, ty. So tx, e to the tx over ty plus ty sine ty over tx. And in the two fractions, the t's cancel out, and we're able to factor t to the first out of both of these terms. And we're left with t to the first times what is our original function. So this function, f of xy, up here, is homogeneous. And if we have an equation of the form one function times dx plus another function times dy equal to 0, where m and n are both homogeneous functions of the same degree, then we call that a homogeneous differential equation. And if we have a homogeneous differential equation, we can do a substitution that will turn it into something that is separable. So we're substituting y equals v times x. And by doing that, the function will turn into a separable differential equation, which we've been working on. So we want to find the general solution here. First, we have to look at whether or not m and n are homogeneous. So we start with function m, and then we plug in tx and ty. So m is homogeneous of degree 2. Then we check the second function, the thing that comes before the dy, and that would be 3xy. And we plug in our tx and ty. And n is also homogeneous of degree 2. And what that allows us to do is make the substitutions y equals v times x and dy equals x dv plus v dx. And that's just using the product rule to differentiate. But we're changing this equation to become an equation that involves x and v instead of x and y. So we're going to have x squared plus v squared x squared, that's y squared, times dx, plus 3x vx times x dv plus v dx equals 0. And now we're going to go through and we're going to simplify and separate our variables. Since this was a homogeneous differential equation, I'm telling you we will be able to separate these. And then there's actually some like terms here. we have x squared dx plus 4x squared v squared dx. And then I'm going to move the dv term to the other side. Thus begins our separation. On the left side, we can factor out x squared dx, leaving us with 1 plus 4v squared equal to our negative 3x cubed v dv. And we're almost separated. I'm going to divide both sides by x cubed. And 1 plus 4v squared. X squared over x cubed is x. And then I get negative 3v over 1 plus 4v squared dv. Now we have our variables separated. Now we're going to integrate. Natural log of x equal to, and we're going to have to use a u substitution, so du is 8v dv. And then, of course, we have our plus c. And I'm going to clear my fraction here. Multiply both sides by 8. And then, since c is a constant, I can really just think of that as being the natural log of some value. I'll call it d. Natural log of d is a constant c. And what that allows me to do is I can use properties of logarithms we have the log of that product equals natural log of x to the 8th. And now since we have natural log equal to natural log, the natural logs go away. We get x to the 8th is equal to a constant d times 1 plus 4v squared to the negative third. And this is a solution to that differential equation. But the original problem didn't have v in it, it had x and y. So last thing we have to do is do a substitution. X to the 8th is equal to our constant d times 1 plus 4. We had substituted y equals vx, so that means that v is equal to y over x. And this is a solution in terms of x and y of our original differential equation. If you compare this to the problem in the text, this is slightly different. I had copied the problem down wrong, but it's the same idea. And the book goes a little further to do some more simplification with this, but this would be simplified sufficiently for all intents and purposes. Second problem we're going to look at is this one where we have the rate of change in the number of coyotes being directly proportional to 650 minus that population. T is the time in years. So what this means is we can set up the differential equation dn dt equals k times 650 minus n. And this is not a differential equation that we have to worry about homogeneous or not. We can look at this and see that this is a separable differential equation. We get dn over 650 minus n equals k dt. We integrate both sides. And we get natural log of 650 minus n, but negative if we do a u substitution. This is equal to kt plus c. And in an effort to simplify things, we can move the negative to the other side. Natural log of 650 minus n equals negative kt minus c, and now we can change to exponential form. E to the negative c is just another constant. And we can subtract 650 and divide by -1, giving us the population equation n equals negative ae to the negative kt plus 650. And now we can use those initial conditions that were given to us to find a and to find k. We can start with plugging in t equals 0 and n equals 300. E to the 0 is just 1. So a becomes negative 350, positive. If we plug in t equals 2 and n equals 500, we can solve this and get that k is approximately 0.4236. So our population growth equation is n of t equals negative 350 e to the negative 0.4236 t plus 650. And this model is modeling the population of these coyotes, and we could find any population for any given t value at this point. Your assignment, the problems you should work on in 6.3, is 17 through 20 and 37 to 43 odds.